Okay, this is now another integral we need to solve, but there's no trigonometry involved. Initially, we're going to see that the best way to figure this out is to find the partial fraction decomposition of this expression. So I start with x squared plus 1, and then I have to find the partial fraction decomposition. Write this as a over x plus, because x squared plus 1 is irreducible, I can't write that as linear factors, as a product of linear factors. I have x squared plus 1, but then the power can't just be b, or the numerator can't just be b. It has to be bx plus c. It could turn out that the x part never shows up. It could happen. That is a possibility. But I always have to consider the possibility that it doesn't, that I have both bx plus c at the top, or cx plus d, or dx plus e, whatever else it turns out to be. So I have to find a, b, and c, and I do that by multiplying both sides x squared plus 1. So I use distributive property when I multiply this by the first term on the left side. The x cancels, and the x squared plus 1 cancels, and I just get 1. Okay, so I have 1 equal to on the left side, and I'll multiply these. So the x's will cancel, this will be left over, and the a will be left over. So that's a times x squared plus 1. And then when I multiply this last one, the x squared plus 1's cancel, and then the x is left. So I have bx plus c, all that times x. Now there are several ways how people solve this. Famously, sometimes people will choose to plug in the roots of this. So for example, plug in x equal to 0 to find out what a is, and then plug in, like there's nothing to plug in here, maybe I or something. But there's no real value you could plug in here to make that 0. So you'd have to do something else to figure it out. So I will avoid plugging in values just to solve this partial fraction decomposition in a most straightforward way that could be replicated in all cases. So that way is to expand everything. This could be a little too much work in some cases, but it will work almost all of the time. And then you group the like terms. So you have x squareds, so a plus b, x squareds. Grouping these two, right, you get that. You can see that a x squared plus bx squared is what you get. And then the x term, so cx, and then plus a. And now you start comparing the two sides. So how many x squareds do you have on the left side? None, right? So that means there can't be any x squareds on the right side either. So a plus b has to be 0. How many x's do you have on the left side? None. So you can't have any x's on the right side either. So c needs to be 0. Started to find some information already about c. So we know c is 0. And then finally, how many numbers, independent terms, do we have on the left side? That's 1. And then on the right side, we have just a, terms without x, the independent term. So we have a equal to 1. Found another information. And then once you go back to the first equation, 1 plus b, it's got to be 0. B is negative 1. So all of this is not calculus. All of this is just algebra or pre-calculus, or whatever class you took where you learned partial fractions. So this is the partial fraction decomposition. And that reduces the problem into the integral of x squared plus 1. So we now have a over x as your first integral, so 1 over x. We have just solved this partial fraction decomposition for a. And then bx plus c. C is 0 and b is negative 1. So this will be minus 1 x, right? X squared plus 1 dx. And that's because b is multiplying x. So this is why I have this. And then plus c is going to be a plus 0 in here that I'm not going to bother writing. So now these are the two new integrals that I need to solve, which are significantly easier, or I should even say possible. I don't know how I could solve the original one without doing this. So here's the trick on this one. The antiderivative of 1 over x, pretty easy, ln absolute value x. And the second one is going to come out a similar way. You just have to make a u substitution. So if you call u equal to x squared plus 1, then du is 2x dx. So 1 over 2 du is x dx. So you can write this x dx here as 1 over 2 du. So you turn out with a minus 1/2 on the outside, and then 1 over u du. And that is another easily solved integral. It is the ln of the absolute value of u du. Let me be careful about this. Plus c. And then remember what u is. U is x squared plus 1. And just as a final touch, because x squared plus 1 cannot be negative, the absolute value is actually unnecessary in this case. You still need it on x, but on x squared plus 1, you don't need it. And this is the answer. Now, this could be changed very much so if the partial fraction decomposition were different, if that were not a x and if that were a 1, right? If that were a 1 over x squared plus 1, you also need to know this integral, right? And this is the arctangent, or the tangent inverse of x. So make sure you know this for different problems, just in case you need to use that as well.